of it being test week is let's do some math. So we're talking about familiar things, but we're looking at them in a new way. So we've been talking about functions, and then we introduced, especially on Wednesday, this very important type of function that shows up in all areas of mathematics. Some of you are familiar with it from your days in calculus, and that is a sequence, which is a very special type of function. And so anyhow, not only do you have to be familiar with these sort of properties of functions like one-to-one and on-to and this idea of a bijection, we also want you to be able to understand those connections with the stuff that you're familiar with functions. Someone pointed it out last week, I forget who it was. So I apologize, but if a function's increasing, is it one-to-one? And the answer is yes. But can you show that, right? Can you prove that? So one of the things I would highly encourage that you try to think about if you're looking to gain anything from these topics is when you think about one-to-one and on-to and bijection, and you think about sequences like we've talked about Wednesday and we're going to talk about now, try to put these new ideas in their place with the stuff that you've done before. So one of the examples I suggested that you ponder is when you were in an algebra class at some point, whether you remembered it or not, you talked about inverse functions. That is standard high school math curriculum. And one of the things you were taught, whether it was taught effectively or not, is there's this thing called the horizontal line test. And they said if a function passes the horizontal line test, it has an inverse. Now that is a very unscientific or unrigorous way of saying that if you are one-to-one, you have an inverse. So what I'd ask you to do is think about what this horizontal line test from your algebra. I'm sorry, I keep taking this off. I apologize. Scorn me. There's no shield here, so I'm not supposed to take this off. And it's also not fair if I take it off and you don't, right? That's not nice. Shame on O'Grady. But what I'd like you to do is think about those kinds of topics from previous courses and try to let the new ideas resonate with them. Now, I'm not saying you have to do this, but I think if you do this, it gives you a better chance of understanding these new ideas. Because let's be honest, the first time most human beings learn about one-to-one and on-to, it makes no sense to them. And remember, a function is sort of this relationship. And so a one-to-one or an on-to function is a very special type of relationship. And that means those relationships have certain properties that we can take advantage of certain times. And so we want to know when we can do that. All right, so anyhow, as I said, there's a new homework up. So let's look at the problems and let's do some math together. And let's think about how we can help you learn how to solve these problems. So I do believe, yes, it's there when I go on Canvas. Everything seems to be in a good place for us. I'm pulling it up on my other screen here. Come on, today, Junior. It's not opening. No, well, that's standard. I don't know why the internet in this room is so packed. You would think this would be the best internet room on campus, right? It's the computer science. It's really not worried. This is quite fascinating. Okay, so while we're waiting, I'll talk about the problems because I know what they are because I gave them to them. So questions you might want to ask yourself. Do you remember what even and odd functions are? Can you define them? Now, I didn't actually say yesterday, or excuse me, last class, here's what an even function is, here's what an odd function is. But I also told you that I'm skipping some of these things about functions that you have seen in numerous courses. You've already seen this long ago in a course. Now, you might forget what it is, but you can easily Google it. You also know that if I give you two functions, you know how that you can add them in a natural way. You can subtract them. You've been doing this before. Things like terms. You can multiply, distribute, all that kind of stuff. So I'm not going to sit here and write all those definitions down. That'll bore you to death. But you do need to find these things somewhere and be able to work with them. And so can we do that? So for example, what does even mean? I'm not going to write down all the specifics, but there's two sort of things that matter here. Even means f of x equals f of minus x, or negative x, for all x in the domain. And then odd means that if you plug in a negative input, it spits out minus what happens if you plug in the value without the minus sign in front. So these are sort of like wishy-washy quick definitions, but in fact they are important. So a question you might ask yourself, or at least maybe you won't, but I'm going to ask you to ask yourself, what can you say about even and odd with respect to one-to-one and onto? So what I mean by that is, maybe can you think about this and can you formulate something you think to be true or not to be true, and can you verify? I kind of did that for you on homework 1. I actually told you to prove that it's impossible for a function that's even to be one-to-one. But can you prove that? So remember the thing, think about a famous even function, and one of the most famous even functions there is y equals x squared. It's a very simple. And right now you should be, oh yeah, even. That's when those fools in high school were telling me to do things like symmetry around the x or the y axis, and yet all these things they wanted you to learn, and shifting left and right. Remember you guys learned all that stuff long ago, and you said, I don't remember, and this is pointless. Maybe it is pointless, I don't know. But if you put this new stuff in that context, it might give you some ideas. So, can you answer questions, or can you, let me say that more specifically, can you formulate something and verify that it's either true or not true? So I asked you to do that, but I gave you the thing. If you look at problem 1 on the homework, I asked you to show that you can't have an even function that's one-to-one. Under certain sort of, if it's going from, say, for example, the integers into the integers. So there's another subtlety here that I've mentioned this before, but when you talk about a function comes sort of as like a triple. It is a domain, it is a codomain, and then there's this role or this relationship that we have between them. So we tried to make this clear last week that being one-to-one or onto often depends on the domain and the codomain. That is, if I choose different domains, I might go from being one-to-one to not being, or vice versa. So part of what we're asking you to do on the homework is understand that. Does anybody have, I'm assuming you don't have any questions about the homework, obviously, because we didn't, I just posted it a little while ago. But does anybody have sort of anything they want to say about what's on the screen right now? Going once, going twice. So, and here's the other thing that I know I always sound like a big jerk when I continually say this stuff over and over again. But if you don't spend a lot of time on this, it's really hard to learn. And there's a ton. I mean, look how much we're responsible for, and we're really only through not even 2 chapters in this book. And there's a ton that you are technically responsible for knowing. So I wish I had nice, simple, like I can give you a pill and then you wake up tomorrow like, oh my God, this stuff is so easy. But I don't have that, do I? It'd be nice if we did. It'd be really nice. Okay, so what's that? Oh, I don't know if you have a question. I can't tell if you're I'm not even trying to be mean. I don't know if you're saying something or if you're telling her something, because I can't, with the sound muffling. So I feel bad. I never know if people are asking questions, what's happening. Okay. All right. You giggled. That's all right. Fair enough. Fair enough.
Yeah, I giggled.
Okay. Very good then. Another question that you might want to ask yourself for these functions. So here's another question. So do you understand the difference between codomain and range? This is a very important thing. Do you understand it? So let's look at an example to help illustrate this. So I'm going to take f and I'm going to say it's defined from the integers into the real numbers. And let's say it has a formula the following way. Let's say it's f. And let's say that when you plug in a number, it spits out 1 divided by that number. So the domain here, by definition, is the integers. The codomain is the real numbers. Now, what is the range? The range is slightly different. Well, we have to ask ourselves, what do the guys look like that get spit out? Well, what am I allowed to plug into this thing? I'm allowed to plug in any integer. So I can plug in 1. I can plug in -1. I can plug in 2. I can plug in -2. I can plug in 3. I can plug in -3. So my range is a little different to describe. My range is a set of all plus or minus 1 over, let's say, n, such that n is an integer. You could write this slightly differently if you wanted. You can write this, you could spell it all out. You could say plus or minus 1 plus or minus 1/2, plus or minus 1/3 if you wanted. You might want to spell out even differently. You might want to write it like this. Ellipse, and then say like -1/2, -1. But then when you do it this way, you kind of lose your ordering. So you're like, well, that's kind of weird. So this last way seems kind of weird because it's kind of not in sort of like an ascending order, right? So again, what I'm saying is what might be a little uncomfortable about these two representations is they don't seem to have sort of some sort of order to them. Maybe that, should we accept those as good sort of notations, or should we stick with this particular thing? Something for you to ponder. Notice that 0 is not defined. So then the question is, excuse me, 0, I mean, the f of 0 is not defined. So then the question is, when we write the domain is the integers, are we lying? So that's a question I want you to think about. Should I write z here, or should I be more specific and say z take away 0? See the subtlety now. Okay, so again, I want you to ponder this. The domain is the integers take away 0. Why? Because I cannot put 0 into this function. One of the things that you see this, but it's not really ever described in detail in other classes, but we sort of use this same calculus you might remember doing optimization problems, where we say, okay, let's find the dimensions that minimize or maximize something. And what we were using, why that was a legal way of using it, and one of the things we made you, at least if you wanted full credit to, is you had to realize that there's this theorem that tells you that you have an absolute maximum or minimum, because you were restricting the domain to things that made sense for that particular context. For example, if I'm talking about the dimensions of some geometric object, it makes no sense to talk about negative length, right? So we can assume in that context that, say, the domain that we're interested in, or the domain, as we say, of definition, would be, say, 0 to whatever a reasonable number would be. For example, if I know that my perimeter is, say, 100 yards, well, then I know that the length of my rectangle can never be larger than 100. Does that make sense? Maybe. So oftentimes, depending on context, we restrict our domain for certain things. So we have to be very clear about that, not just because it is or it is or isn't defined, but also because of context. Some of you have seen this sort of issue, actually, that this problem's pointing out, and maybe you don't. If you go to a calculator and say, what is 1 divided by 0? What does the calculator tell you? Well, it depends on what kind of calculator you're using, right? Some calculators might say it's undefined. Some might say air. Some might tell you it's infinity, which is, then you start having nightmares of what does that even mean? Another thing to keep in mind when we're talking about these domains and codomains is not just functions that you're familiar with like this, but also functions that might be used in, say, computer software. So if we say we have a function that picks the youngest child out of a family, well, does that function make any sense if we have a family that doesn't have a child? Think about that. So what we often do is we give this, and just for context here, we often call this a sort of what's called a partial function, because what I've written here, I should have been more clear, because when I write f colon integers in the real, there is this subtlety that I cannot plug 0 in. Does that make sense? So what we really do is, here's sort of the way I want you to think about this. If we write f from, say, the integers into R, then f equals 1 over n is called a partial function. And then if we write the more correct notation, f, say, take out 0, now this is completely legal. So there's a subtlety here. Keep that in mind. So to go with this sort of thing, suppose one of you graduates and then you work for some company. Maybe you work for a university and you design software, databases or something. So let's think about this function. So let's just use generic letters for now. What about f from A to B, where f assigns employees of a certain company to a number which is their salary. Questions you might ask yourselves. What are possible sets, or what are, let's say it this way. What do possible sets A and B look like? I'm not, there could be more than one. What do they look like? And then you could ask, is F ever a bijection? That might be something you want to know. And then more importantly, why or why not? So again, I'm not doing an example here. I'm asking you to think about this scenario. Do you get the difference here? One of the skills that you'd kind of like to gain in a class like this is to not necessarily always think of, say, these new ideas like a function in terms of what you're most familiar with. It's helpful to use those examples from like algebra class and calculus class. But what you need to understand is that a function can be much more abstract than that. A function, by definition, takes one set A, takes another set B, and has a relationship between the two. The only condition is that there's a uniqueness here. Every guy in A only gets one partner in B. It can't get more than one. Does that make sense? So you might say something like, okay, what is A? Well, A is the names of all the employees, right? Or maybe say A is instead of names. Maybe A isn't names. Maybe every employee has a number, just like you have a student number, right? Maybe they assign your student number to a number, or excuse me, the employee number to a number, which is maybe their salary, right? So A could be a list of names. It could be alphabets or names in the alphabet. B can be numbers, right? So think about the different scenarios you might have here, and then ask yourself, in these scenarios, is it one-to-one? Is it onto? Why or why not? And those answers can change depending on what you decide A is going to be. Maybe you want to have some sort of security in your company. You don't want people to know everybody's salary. You don't want someone in HR. So maybe instead of using their names, you use something else, some numerical thing. Maybe their social security number, employee ID. I don't know how you want to do it. Now compare this example with something like this. So to compare the above with, if I take F from, say, R to R, so now we go back to some more familiar places. What if I take this function? We'll make it look ugly. Is this a bijection? Why? Why not? So let's think about this particular problem in depth. Let's do it together. Again, I can't do every example you guys would want to learn. I can't. We would never get out of here. So we got to pick and choose what we do. But let's think about this. Is this a bijection? Do we think it is? Why or why not? And then can we verify it? So again, you don't solve these problems. This is not you know, algebra 2 in high school. You don't say, oh, looks like it's a quadratic formula, let me plug the numbers in. That's not how this works. Now, there are some themes that you will pick up on, no doubt. So the first thing I like to think about when I want to know if something's a bijection or not is I ask myself, okay, what is the graph going to look like? Now, that only makes sense if I have a function that's traditional in the sort of the sense that you're familiar with, like this, with an explicit formula. So the first thing I say to myself is, okay, I know I can get rid of things right away. I can make conclusions right away. Anytime I have a rational expression, is the denominator ever 0? Because I know if the denominator is 0, then I have an asymptote, and then I know that there's going to be things that I can narrow down right away. But when I look at this creature, I notice right away the denominator is never, ever, ever 0. Now, depending on how much calculus you remember, you might be able to get answers real quick here by thinking about what the graph looks like. You might say, oh, I know exactly. I can take some limits. I can do all kinds of stuff like that. But let's assume right now that we don't think that way, and we want to just think strictly with the definition of one-to-one and on-to. So here's how I would attack this problem. Let's do this. Here's my strategy. So I am going to brainstorm first. I've talked about this many times with you guys now. You ain't just writing a solution up. You got to brainstorm. So the first question I'm going to ask myself is, can I get two? Let me phrase it this way. Can I get two different inputs to give same output? Because that's what one-to-one's all about. One-to-one means that the only way I get the same output is if the inputs are the same, right? So my brain is very excited right now because I think this is going to be a quicker problem, because what I see is I see 2x squareds. And x squared is like a siren all the time, because we know that anytime I put -5 in, I get the same output as if I put 5 in. Right? So anytime you see even powers, you should be thinking it's possible that this thing is even, and hence it ain't going to be one-to-one. Do we understand that? That's what I'm thinking right now. I don't know that. And so here's what I just do on my next line. I'm like, yes. Note, f of, say, -a is equal to a squared plus 1 over a squared plus 2, right? And that's the same exact thing as f of positive a. And this is true for any a in the real numbers. So right away, what this means is, this means f can't be 1-to-1. So of course you're going to say, I don't understand what that means. Well, because what the difference right now is I know what the definition of one-to-one is. You likely don't. Because like most students, what you likely did since last Wednesday is not open a book here for this class, because that's what students do, right? You say, oh, there's nothing due Monday. Why in the hell would I read my math? Why would I want to learn anything? I know, I've been there. So right now, you guys don't know the definition of one-to-one. You don't know that it means, okay, one-to-one is, no, that means that f of a, equals f of b when a equals b. Or equivalently, it means if a does not equal b, then f of b cannot equal f of a. So in words, it means what I wrote on the previous page. If two different inputs gave me the same output, that means it's not one-to-one. And there are infinitely many examples of this. -1 and 1, right? -2 and 2. In fact, negative any real number, -1/15 and +1/15 spit out the same number. That means it's not one-to-one. Now, it remains, what about onto? Now, onto means you pick any guy out there in the codomain. Then there has to be a corresponding input. That's what onto means. Now, in terms of graphs, that means the graphs, the y values cover up the codomain. So that's oftentimes something that's a little sort of difficult for us to understand the first time around, but let's write this out in English. So for onto, let's pick an arbitrary real number, and I'll call it y. Here's what we need. We need an x such that f of x equals y. That's what we need. So let's ask ourselves, let's reason, is this possible? So again, I am using the definition of onto. I remember it. I learned it many years ago, probably after I flunked it the first time or two on a midterm, like many of you will flunk over the next 3 days, right? Not very, you know, I'm kidding, of course. You guys, you've had me before. You guys know. Well, sort of. All right, so here, let's ask ourselves, is this the case? So we go to the next page. That's the same thing as asking, is there a solution to this? So does this equation have a solution? And in particular, we know it has to be unique. Because if it's not unique, then we don't have a function to begin with. So think about how you'd have to do this. What this means is you'd have to find out what is x in terms of y. So this is like an algebra problem now. Can you solve for x in terms of y? So let's look at this. And again, I'm brainstorming. I'm going to rewrite like this. This is the same as x squared plus 1 equals y x squared plus 2y. So I'm doing a little bit of algebra. I multiplied, I cross, what do you guys call that as kids? Cross multiplying. What I did is I multiplied both sides by the denominator so that I can clear the fraction. And that is legal because x squared plus 2 is just a number. Okay, now I'm going to try to solve for x. If I rewrite this, I can bring this to the other side. I'm left with x squared minus yx squared is equal to 2y minus 1. And then, of course, now I can factor out an x squared, and I'm left with x squared times the quantity 1 minus y is equal to 2y minus 1. And then the last thing I'm going to do is I'm going to divide both sides by 1 minus y, and I get x squared equals 2y minus 1 over 1 minus y. Now, you might say, well, why didn't you take the square root? Well, I don't even want to go that far because I know that I got some fiascos happening here. If the number on the right-hand side, if I choose a y, notice I said y was just some arbitrary number. But suppose for the sake of argument, I chose y to be, I don't know, 1. Does 1 make sense here? No. And if I choose any y that makes that right-hand side negative, that's bad news. And what I'm really hoping for now is that someone says, why the hell did you go through all that? You could have made that conclusion without any algebra. And then I would say, you're finally friggin' learning. Did I have to do any of this? No, why? Why could I have stopped with the first sentence? Because if y is any negative number, it's impossible for that to work. If I pick y to be 0, can it work? No. If I pick y to be negative 1, can it work? And if you're still confused, look at this. My point being is, if this number happens to be 0 or any negative number, then this sentence is ridiculous because the left-hand side is always what type of number? I'll give you a hint. Starts with a P and ends with an if. Positive. It can't be negative. Do we follow me here? So again, it was okay that I did this algebra. And then I came to the same conclusion I could have come with earlier. And that is the key thing here. So even if I go back to the previous page, even if I didn't do any of that algebra, what I can know right away is that this function right here only spits out positive numbers. And that means since its codomain is R, the range is 0 to infinity, not including 0. That ain't R. And so since the range and the codomain aren't the same, we can't be onto. Thank God, what a time to be alive. What a time. There's so much to learn. Not enough time to do it, is there? It's so sad. So sad, so sad. So there's a few ways we could have made this. We could have made this claim. What we did is not wrong, but we could have come to this conclusion much quicker. Because all we had to do is say, oh no, and here's a similar way of doing it. So the above reasoning shows F can't be onto. So let's remind you why. Why? Well, say y equals 0, which is clearly a real number. There is no x in the real numbers that satisfies this. If you can find an x that satisfies this in the real numbers, I will shake your hand. We'll march you out to like Harvard or something. They'll give you a PhD. You probably won't even get a PhD. They'll just let you teach forever. You can travel the world telling everybody how you solved this with a real number x. You'll be famous. like Einstein. My advice is for you to really pay attention to these examples and try to understand them. They're not easy topics. On the one, one-to-one and onto, good God. It's just not easy. This stuff is difficult to learn. I understand that though, and I just hope you appreciate what I'm trying to tell you. And does anybody have a comment, question? Yes, you have a question? I thought you did. How about anybody at home? Huh? Good old midterm week. See how I do this? It's midterm week and it's stress for you. So what I do is I just give you a take-home test. So you hate me the least out of all your other professors. Yeah, and you say he's not terrible. Yeah. Let's check the Twitter machine and see if anybody else got the Roni.
My mom went to a wedding this weekend.
Did she?
And in Nashville.
In Nashville? That's like going into the fire.
And look, this country singer showed up to do like their
Really?
yeah, they're like.
Well, that's all Nashville is the country. No, have you seen your mom since then? Huh? Mm-hmm. How come you didn't go? That's a shame.
I don't really like. I know the family.
I actually have people. I shouldn't say this. I'm on recording. Never mind. All right. People know what my friends and family are doing. All right, or do you? All right. We're going to switch gears slightly, but let's talk about some other functions that come in the terms of what we said sequences. So. So we've also been discussing sequences. And so we've given you a few examples of this. And so there's lots of things that are familiar to you here. But there's one that you probably aren't too familiar with. And so I'd like to sort of talk about that. And it also comes out on your home, one of the problems on your homework. So most of you are capable of listing terms of a sequence. Like that's usually something students don't have a hard time coming with. But when we start to ask you to study certain sequences that aren't defined necessarily explicitly, but are defined, what we say, recursively. So here's an example. So many of you have seen the factorial before. What we're going to do, though, is study it from two ways. So we're going to define it two ways that are equivalent. So the first one we're going to say is an explicit definition. So for n in the natural numbers, n factorial. So for those of you who haven't seen this before, it's n with an exclamation point. It's a very important sort of, well, it's a number, but you could think of it as a function because what it's doing is it's taking a number and assigning a number to it. So what is this? By definition, we can define this as n times the number that precedes it times the number that precedes that guy, all the way down to 3 times 2 times 1. So that is an explicit definition for the factorial. And then we also define 0 factorial as 1. Now, there's lots of reasons to do that. Some of you might know them from calculus, others might not. But right now, you just have to say, okay, that's a good definition. I could say 0 factorial is cat if I wanted. I could say it's dog. I can say it's turkey. I could say it's key fob. I don't care, 0 factorial. It turns out to be very useful to define it to be the number 1. Just like when you discuss exponents, you say, okay, x squared means x times x cubed means x times x times x. Then we have to decide how do we define x to a negative number? Or how do we define x to 0? And it turns out there's lots of ways to do it, but we all agree that let's define anything to the power 0 to be 1, because it helps all our rules be satisfied, our exponent properties, if you will. So you just have to just trust that we'll define it this way. And then another way to do this is a slightly different way, so we'll change colors. Another way to define it is we can define it what we call recursively. We start with 0 factorial equaling 1, and 1 factorial equals 1. And then for n greater than or equal to 2, n factorial is just n times the previous factorial. So this is completely equivalent to the other way of defining it. It's just 2 ways to define the same thing. You get the same numbers either way. So this one might seem a little bit, odd, but then you might want to ask yourself, what would be a more efficient way for you to compute these by hand? And then you might ask yourself, what would be a more efficient way for a computer to do them or a calculator to do them? See, these are things we often don't think about when we're doing certain math. We don't think about that these things might be used in completely different ways when we're writing maybe software, where we have to do lots of counting or we have to do quick arithmetic. So let's just look how this works using this definition. So we know that 0 factorial is 1. We know that 1 factorial is 1. 2 factorial, by definition, is 2 times 1 factorial, which becomes 2 times 1. What is 3 factorial? Well, this is 3 times the previous number factorial, which is 3 times 2 times 1. And then 4 factorial is 4 times 3 factorial, which is 4 times 3 times 2 times 1. So it turns out to be the same exact number. It's just 2 different ways of computing it. Think about this. If I go to, if I kept this sort of pattern going, what is, say, 100 factorial? Well, one way to write it is 100 times 99 factorial. Now, it might be helpful if you put parentheses here so you guys sort of understand the grouping. And then you could say this definition versus this definition, which is 100 times 99 times 98 times 97, and then that goes all the way down to 3, 2, 1. Two ways to define the same thing. So this would be a good exercise for any of you who have a little bit of programming skills. Go to Java or any sort of computational thing and set a timer. What does it compute 100 factorial quicker? If you define it recursively or if you define it explicitly. Maybe we'll give you guys an extra credit assignment if anybody wants to tackle that. Of course, I can always just go to the web. No, I don't want to lose share. I want to pause share. Hopefully, are you guys seeing? Yeah, you're seeing it there. If I go to Google and I just type 100 factorial, it'll probably tell me what the number. Oh, it rounds it. That's a big round job there. That's a big number, isn't it? Let's go to Wolfram. Wonder they won't round it. See, notice that this number does have a bunch of zeros at the end of it. But I do believe Google rounded. I could be wrong. Yeah, they absolutely did, because they rounded up like 150 spaces. I mean, this means 9.332622 times 10 to the 157th, right? So what Google's doing is they're rounding, which is okay because that number's so big it doesn't matter. But we clearly see there's more than just 6 non-zero digits here. But the question is, can you get a computer to do this? And if so, which way's faster? And you might be kind of like, what does he keep talking about faster? Well, think about humanly. What would you know? In order to use the recursive definition, you have to have the previous number sort of stored, right? If you want to know what 7 factorial is, you need to know what the first 6 factorials are, correct? Here's another way to think about it. And this is on your homework as well. And some of you have seen this before. Let's define S sub n to be 1 plus 2 plus 3 all the way out to n. So it's easy, and when I say easy, I mean it just requires algebra. It's easy to show that S sub n is equal to n times the quantity n plus 1 over 2. So why am I even making an effort to point this out? Well, we need to ponder this. And again, most of you have seen this. If you took calculus before, you've seen this. No doubt in my mind. So let's think about why this is important. If I wanted to add up the first 100 numbers, if I use just the pure definition of adding them up, how many operations am I doing? Well, 1 plus 2 plus 3, that's a lot of operations. If I use this shortcut, I am doing how many operations? Well, I'm adding n and 1, so that's 1 operation. Then I'm multiplying that times n, so that's 2 operations. And then I'm dividing by 2. But really, it's even simpler than that, because if n is up in the numerator and the guy who comes after n is also up there, one of those numbers has to be what? Even. which means one of those numbers is divisible by 2. So I ask you, what would you rather do? Compute 1 plus 2 plus 3 plus 4 all the way up to 100? Or would you rather take 100 times 101 divided by 2? What would a computer rather do? So again, let me put this in terms of maybe language that's a little easier for you to understand. What is, like, say, S of 74? S of 74 is 1 plus 2 plus 3 all the way out to 73 plus 74. Or you can say S of 74 is 74 times 75 over 2. What would you rather do? What would a computer rather do? So the point I'm trying to make in not just this example, but the previous one, is to think about operations necessary to do something. Does anybody have a question? And by the way, these are examples of functions. Okay, the last one that I want to point out, because it's also on the homework, is one that you've sort of, again, some of you have seen before. And so let's do another one. Let's call, I don't know, I'll call it R sub n. Let R sub n be 1 plus 1/2 plus 1 over 4 plus 1 over 8. And so the pattern here is that I'm taking 1 over a power of 2. And by the way, we have a very shorthand way of, don't forget that, you know, we're adults now. We have to learn to use what we say is summation notation. And the question that I'll ask you to do, and some of you should know this already, if not, it's not hard to derive or figure it out. Can you get a simple formula for R sub n? And then what is, say, R sub 100? So those of you who paid attention in calculus might remember that this is sort of they're called partial sums of what's called a geometric series. You might remember that there's a simple formula here, and it's not hard. You don't need calculus to derive the formula. The formula itself does not require calculus. And the formula can be derived in very much the same way that the formula for S sub n is derived here. You get creative. So I'll give you a hint for those of you who don't remember or never saw it. Hint. What happens if you compute R sub n minus 1/2 R sub n? Now, here's the hint. Don't try to do it in general first. Do it baby style. Do it baby style. Start easy. And then you'll get the pattern. So for example, if I take, let's start with like the third one. What's R sub 3? R sub 3 is 1 plus 1/2 plus 1/4 plus 1/8. So what is R sub 3? If I take 1/2 in front of it, I get 1/2 times this. Which of course becomes 1/2 plus 1/4 plus 1/8 plus 1/16 if I remember how to distribute. And so then, r sub 3 minus 1/2 r sub 3, what is the only thing that survives? A 1 survives. The 1/4 cancel, the 1/2 cancel, the 1/8 cancel, and the only other thing that left is 1/16. And so what you get is if you take the left-hand side is 1/2 r sub 3, and that is equal to 1 minus 1 over 1/16. And what can you say about r sub 3 then? R sub 3, if you multiply both sides by 2, you get 2 minus 1 over 8. Do you see the pattern yet? If not, go to r sub 4 or do r sub 5. There is a very beautiful pattern here. All right, we're over time. I apologize. Thank you guys very much. Please go check Canvas tonight at 8 o'clock. Start working on the problems that way. You can email me if you have any questions because it's due Wednesday at 4 p.m. You will scan and upload it to the Canvas page. Thank you guys very much. Have an awesome day. Good luck on all your exams. And if you need help, send me an email every hour until I answer. Thanks, guys. Bye.